Hello from me, Lidia Morawska, to all the students and teachers, and welcome to our second webinar of the program, The Air is There, Here and There, Queensland Communities Assessing and Comparing Air Quality. This is the second webinar, and you may remember what we discussed during the first webinar, which was in August. Well, first of all, we talked in a very general way about air pollution, its sources, and particularly the impacts of air pollution and on health and climate. We also had a little insight from one of the students. What does good air quality means to the students? We've also heard from a lawyer about everyone's right to clean air. We've heard from the curator of Queensland Art Gallery of Modern Art of the plans for an exhibition next year on air in the art. This was very interesting for me as well. And finally, we've heard a little bit about the koala monitor, the monitor or monitors which are installed in your schools. So we started this as a background. Today, we are planning to talk a little bit more about the koala and exactly what does it do. And in the context of this, we'll talk again a little bit more about sources and composition of air pollution and what happens to the pollutants in the air. We'll learn how complex all of this is, how many pollutants are in the air. And this brought us to the question what to measure for our little monitor. So how did we decide what to measure? And finally, we'll look at the data from your school. So reintroducing the koala. You've heard that the abbreviation for this monitor is knowing our ambient local air quality. So this is the koala, and I hope that everybody has seen the koalas hanging in your school. So air gets into the koala from two directions, and then it goes to the sensor, CO sensor, a particle sensor. Well, it's got a, as you can see on this photo, a 3G modem for communication and a few other things, a battery switch and so on. A very important aspect and part of the koala is solar panel, because this means that the koala can operate without being plugged to electricity. So this is the koala. However, we didn't talk much last time about what happens with the data which the sensors in the koala, which is CO2 sensor and particle sensor, which they collect, how we access this data. Now, this 3G modem is the starting point for this. So this, how it happens. We've got the data management center in the Amazon Web Services. So this is in the cloud. I'm sure you've heard about this concept that the data or information is stored in the cloud, which is not in an individual computer or a server of an individual institution like a server. I'm sure you have a server at your schools, but it is in the cloud. So this is how it works. Here we've got a koala somewhere there, and the koala sends the data to the cloud, to the Amazon Web Services. Here the data is stored, and the data is also processed. We can do all kinds of things using this data management center, including visualization of what we want to see. So this is in the cloud, but then how we see what's there. The data is transmitted to our computer, to a laptop, desktop, or to our phone, and we can look at the data or the visualization from our devices. So this is a very important process. The data is also stored in the individual koalas, but if we wanted to use it this way, it means that we would have to go up there and take it apart and then transfer the data to a device. This way we can do it without touching the koala or being far away from the koala. We've mentioned to you how the koalas are manufactured, how they are calibrated, how they are compared, how they are tested. So this is quite a process, like a little factory in a way before the koalas are released to the world, if I can call it this way, and operate in different locations. We have or had many different networks of koalas operating in Australia and overseas, and several of these networks operate right now. Now, there are different types of koalas. What we are talking here is stationary, solar powered, so that koala instead, like in your school, somewhere outside. But there are situations where this is not possible, in that sense that the koalas are in shade, never receive the sunlight, which means they will not be, the battery will not be charged. Like, for example, in this project in Melbourne, I'll mention it in a moment again, they had to be facing this way on a balcony, and they were not receiving sunshine. So these koalas were powered from the mains. Now, koalas also travel on buses, and here they are powered from using solar battery. And there's also a wearable version of the koala, like this one here. Now, this one is equipped in GPS, so this way we can tell where the koala has been, and therefore relate the concentrations the koala recorded to the locations. So as I said, we've done many different measurements, many different projects with the koalas. You may remember that last time we've mentioned this particular project, exposure of a Melbourne community to ship emissions. You've seen these images before, so that was the problem, and the community was very unhappy about that situation of the ships emitting and the smoke going directly to the windows. So there were many different ferries, including the Spirit of Tasmania arriving there from Tasmania. Now, what was interesting and very exciting for us, this was one of the first projects, the fact that we were able to, in real time, not only see the data that predict what was going to happen. So we were looking at the data at the data management center. We also knew the timetable of the ferries, and we knew or checked what was the meteorology at the time, which is the wind directions. So see, we were then looking at the data, and we were seeing at this situation here, and we would be were able to tell the residents, saying in half an hour, you will see an increase in concentrations, because we knew that, say, Spirit of Tasmania was arriving, the wind direction was towards the coast, and indeed, in half an hour, we saw a big peak. So not being there, not looking actually at the visual of what happened, but just being able to see this action in real time was quite exciting for us. I'll just mention one other, well, a little joke. We had a network in Sydney of koalas, and this was that spine on the baker situation. We had here's a conversation between Dr. Rohan Jayaratne, who introduced the koala last time to you, in Brisbane, communicating with our colleague in Sydney, John. So Rohan was looking at the data and noticed that there's something happening there around 4 a.m. That's in one of the Sydney's koala. And it was not related to the humidity. When humidity is higher, particularly fog, that fog particles are counted and measured as by our PM2.5 sensor. And as far as the koala data show, all 4 koalas show this, so it's not an instrument problem. So what's happening at 4 a.m. there? And John from Sydney reported, well, yes, there's a bakery, and he provided a name, across the road that must start up the oven to cook bread at 4 a.m. And Rohan's response was, yes, it's almost certainly the culprit, the bakery. But they were a bit late starting up the oven this morning. They started at 4:25 a.m. So of course, this is not, this is a joke, this is not scientifically important information. But the fact that we can, looking at the data from the distance, we can say that something is happening and well, develop an idea of what is happening. So it's not only science, not only application, but I'd say a fan of this. So We've also discussed what does koala measure. So it's the PM2.5 mass concentration of particles smaller than 2.5 micrometer, and CO concentrations, which is carbon monoxide, and temperature and relative humidity. Well, but we didn't tell you why we measure those specific two pollutants. So why this specific pollutants? We hinted to the fact that there are other, more pollutants. So to answer this question and give you a little bit deeper insight into this topic of air pollution, we'll just say a few words about sources and composition of air pollution from the point of view, what is in the air, and therefore what should we measure. Where do pollutants come from? Now, if we were sitting together and if I ask you this question, I'm sure everybody would be able to list all kinds of sources. This doesn't require scientific insight. Fires, as we've experienced, volcano emissions, luckily we didn't, quarry emissions, emissions from industry, emissions from cars. This one, we may be a bit uncertain what this is. Is this smoke? Is this what? Well, remember that I've mentioned that pollutants are formed in the air as well, and this is the haze, particular urban haze. So this is what's depicted on this photo. So the haze is not emitted directly, it's formed in the air. So these are the sources, very roughly, and there are more of the sources, and we can classify them according to whether they are natural sources like soil and rock, forest fires, sea salt, volcanic emissions, or biogenic emissions like pollens, for example, or they could be anthropogenic sources, which means man-made. Vehicle emissions, power generation, other industrial emissions, very importantly, agricultural processes, residential heating and cooking, use of chemicals. We could add a few more to this, but these are the main pollution sources. Now, if you look at this list, you immediately see that there is a type of source which is similar. Vehicle emissions, power generations, cooking and heating. This is combustion. And this is what we've already mentioned last time. Combustion is the most important source of air pollution, anthropogenic air pollution, but also natural if fires are natural. So we'll talk a little bit more about combustion. Well, urban air pollution. So is combustion the reason for urban air pollution? We can say that absolutely transport emissions are the most significant sources of city pollution. And we can come up with many images like this from any places in the world, including Brisbane as well. Can you recognize where this photo was taken? Well, in the valley. For those of you who are not in Brisbane, this is a very busy street in Brisbane with lots of traffic most of the time. So transport is most significant source, but not always. There are other sources. And we know what these other sources could be. We've experienced these other sources, and in particular, smoke from fires, whether wildfires or whether burning for the purpose of clearing the debris in forested areas. Are there any other sources? Well, you probably don't remember this event where when Brisbane looked like this, covered in this reddish dust, where we couldn't see much across the river here. And this is resuspended dust from drying lake in the basically middle of Australia. It traveled this few thousand kilometers to reach Brisbane at these high concentrations. So this happens as well, but these are episodic events. However, transport and car emissions are with us all the time, every day. Pollutants emitted by vehicles. I asked you that question last time, if I remember correctly, how many pollutants are emitted by vehicles? If I give presentations face to face. Before I answer this, I'll ask my listeners, what do you think? Tens? Hundreds? Thousands? Well, it's over 4,000 pollutants as gases, vapors, and particles, which are emitted from vehicle exhaust. And not only from vehicle exhaust, basically from any combustion sources, anything which burns emits this many pollutants. The composition of different smokes of emissions is different, but it means that there are many, many pollutants. Well, I will talk in a moment about this specific pollutants, the gases, but here these dark spots are particles. And we've mentioned about particles last time without going into details about this issue of the particles. But one important point about particles is that modern vehicles emit very few larger particles. And I just stress this, larger with large font, but lots and lots of very small particles. This is quite significant. Now, it's not quite what's represented here because the fact that we see the smoke here, which means that the car is not operating properly. Modern cars don't or shouldn't send clouds of dust like this one. So we don't see anything. If we see emissions, means that there are larger particles, but normally from clean modern cars, we don't see emissions, which means we are dealing with very small particles. So the gaseous combustion emissions, the gases which are emitted, this is the the list of the gases: sulfur dioxide, nitrogen oxide, nitrogen monoxide, and nitrogen dioxide, carbon monoxide, carbon dioxide, hydrocarbons. Now, in this class, there are many pollutants, just not one pollutant, and water vapor. These are the key gaseous pollutants, but there are many more. But these are the key which are the most significant from the point of view of the impact on health and on the environment. And these are the ones which are most commonly measured. Now, but let's talk a little bit about particles, airborne, the world of airborne particles. Now, looking in front of you in the classroom you are sitting, do you see any particles in the air? Probably not. Does it mean that there are no particles in the air of your classroom? It doesn't. I'm absolutely sure that in most of the classroom, the concentrations of particles right now would be of the order of a few thousand of particles per each cubic centimeter of the air. It's difficult to imagine because we don't see them, but to be able to grasp this concept, let's talk about something which we can see and we can imagine. Let's talk about the sand grain and a boulder, big rock. So a sand grain is, well, so much smaller than a boulder. We can still see it. Let's say that we had a task of measuring the sand grain and the boulder. Would we use the same tools? Of course not. We would do it in a different, we would need different tools because of the difference in sizes. The impact, of course, it's stretching a bit what is the impact of a sand grain. If we swallow too many of them, we would be sick. We could be killed by a boulder. But they are worlds apart. You probably would be surprised to learn that the difference between a particle from petrol exhaust vehicle, particle which you can't see, and a dust, something which is on the ground, which you can see, is as big as between a sand grain and a boulder, which means that there are completely different impacts of these particles, and also the complexity in terms of measuring. If we want to measure petrol exhaust particles or any other particles from any other combustion, we would need different techniques than measuring dust. Even so, this is both types of particles are in the air. Now, just to give you an idea about particle shape, and this is in terms of petrol car exhaust particles we don't see. These are images from an electron microscope, and they show how small and how complex these particles are. So this is a 20 nanometer arm particle, and this is basically carbon. And this is how, look, it's got a fractal shape, because the pattern repeats itself. But there are also other particles. This is slightly bigger, 10 nanometers, and this one contains metal. So again, what I stressed before, combustion particles in general are small and light, which is very important. However, dust particles are big, often visible, and heavy. So this is the first element of the complexity of the world of airborne particles. If we were to compare now the particles in terms of where they came from and what they are, we would again see how big differences there are. So this is the big one, it's human hair, about 100 micrometers. This is what we see. Now, bacteria are significantly smaller. We generally don't see them. And there are, in terms of the particles in the air, on the sort of upper sides. Road dust is smaller than this, it's of the order of 5 micrometers. Coal dust is even smaller, 2 micrometers. Viruses are up to about 0.4 micrometer, but could be much smaller. For example, SARS COVID-2 is 0.1 micrometer, much smaller than this. And finally, vehicle emissions are up to about 0.02 micrometer, but most of them are even smaller than this. So they are very small, they are light. So classification of particle sizes. Now, we've already said that we measure PM2.5 and PM10, and this is mass concentration of particles with aerodynamic diameter smaller than 10 and 2.5. Now, mass concentration, what do we mean by this? It means that if we had a filter, imagine a round filter, and we are passing air through the filter, and these particles accumulate, are captured on this filter, and then we take this filter and weigh. This is the mass concentration, and then considering how much air volume we filtered. But there are also ultrafine particles. And here we are, this is the part of that world of the small particles, generally smaller than 0.1 micrometer. Now, we could also measure them on a filter. In fact, we filter them when we investigate PM2.5. But the point is that the mass is so small that it basically doesn't register. So these are called fine particles. They are covered by regulations. We'll come back to this. And now ultrafine particles, because they are so light, they are not measured by mass, but in terms of number of particles per cubic centimeter. That's what I said, and my guess is that there are a few thousand of these particles in every cubic centimeter in the classroom you are sitting. So now put this complexity together, which particle characteristics to measure? Well, I mentioned PM2.5, PM10, PM2.5, that's what Koala measures, but we can also measure ultrafine particles. We can measure composition of the particles, specifically black carbon or metals. You can imagine that they are important and have health effects. Desert dust, like this dust coming from the drying bed, and in areas which are subjected to dust in the outback, this is important. Biological aerosols, for example, pollens or viruses, and finally, secondary organic aerosols, these which are formed in the air. Which one to choose? Well, we'll answer this question in a moment. So what happens to the pollutants in the air? So all these pollutants, whether gases or particles, were emitted by the sources, and we are talking about the combustion sources. What happens when they are in the air? Now, this is a short course on what we call particle dynamics. Imagine two particles floating in the air, and they come together and they make new, bigger particle, coagulation. Particles could shrink or expand as a result of condensation or evaporation. There's particle deposition on horizontal and vertical surfaces. And what is this? This particle goes around. This is transport. If there are any air currents, air flow, which transport this particle around. As you can imagine, this is the transport is important, particularly when we are talking about very small particles. Sometimes you see a leaf or a feather floating in the air. Now, for this to happen, the airflow or the wind must be quite strong. But normally, there is some kind of airflow, and this means that these very small particles basically float in the air. So calculation, particles getting together, making one bigger particles, condensation of evaporation if the particle contain liquid, or if there is moisture in the air, deposition, and on the vertical and horizontal surfaces. Now, I've mentioned last time the concept of primary and secondary pollutants. So primary pollutants are those which are directly emitted, like from this volcano, natural source, from a vehicle, or from industry. So these are all the examples of primary pollutants. And then in the air, due to very complex physicochemistry, including photochemistry, which is involvement on UV sun radiation, they form secondary pollutants. This is really fascinating science, what happens in the air to all these products. Now, there's one very important aspect in all of this, is the impact of meteorology on air pollutants. What this means, meteorology, we are talking about wind, we are talking about rain, which are the main parameters, but meteorology also means temperature and humidity. The most important aspects in terms of the impact on air pollution is precipitation. What does it do? It removes the pollutants from the air, both gaseous pollutants as well as particles. And it's easy to imagine if we have big water drops falling, they will remove everything which is in the air, and the longer it rains, the cleaner the air after the rain is. But there's also the wind, and this is dispersion of pollutants. Now, it's not difficult to imagine what happens if something is emitted and in this strong wind or any wind, then pollutants are dispersed, diluted, so the concentration decreases. So it means that if we are doing any measurements of air pollution and want to interpret the concentrations we measure, what happens, we always need to take into account the meteorological conditions at the time. So with all this complexity, how did we decide what to measure? Of course, I think you have a clear idea now that we couldn't measure everything which is emitted, and there's really no point in measuring everything. So our considerations were as follows. Pollutants, which are most related to health. Of course, all the pollutants are not good for us, but there are those which are even more significant than others. So, and in this list, PM2.5 particles and carbon monoxide are included. And also, we need to take into account for which pollutants there are low-cost sensors, because we could say that we would like to measure this or that, and in particular, we would like to measure ultrafine particles because they are emitted from vehicles and they are the best signal of vehicle emissions, but there are no low-cost sensors for ultrafine particles. So this is the choice, pollutants related to health and sensors, reliable sensors exist. Well, also, we have to consider another aspect, not too many sensors, we could have added NO2 sensors, CO2, and so on. But the problem is that the more sensors we have, the more power we would need to power them and then to transmit the data. So the battery which we have now for the Kala would need to be much bigger. So of course, this would then become much more complicated. So this way, just two, which is manageable, just two sensors, which is manageable for the battery, solar battery we use. But in all of this, we also still wanted to get some idea about the sources, because the fact that we have increase of, let's say, particle mass, is it coming from combustion, for example, an old combustion source? Old in that sense that the particles had time to accumulate, they are bigger and heavier, or it is because this is dust in the air from whatever source. So having this two, PM2.5, which means mass concentration, which is mainly telling us about larger particles like dust, and old smoke, which is combustion particles, but which already got bigger and heavier, and CO, which coming only from combustion, enables us to distinguish between different types of sources. So in this, I also, to finish, I'd like to mention this concept of pollutants related to health. Because at the end, it is, well, which pollutants are related to health, or which pollutants are mostly related to health, or most important. But also, we need then to know the relative concentration, in that sense. If we measure something, is it a lot or is it not a lot? How do we judge? In September this year, the WHO, the World Health Organization, announced new global air quality guidelines. This is the most important document in the world, which in which assessment has been done in relation to the impacts of pollutants on health, and therefore what are the guideline levels, which means how low or we should go to minimize the impact on health. So you can see that among the pollutants, the list of the pollutants included is PM2.5, PM10, that we discussed. It is ozone, it is NO2, which is a gas emitted by vehicles, SO2, CO, carbon monoxide. Now, these all are primary pollutants, apart from ozone, which is a secondary pollutant. You'll see it in this slide, is secondary pollutants. And we've got 2021 air quality guideline values. If you are interested, you can compare that they are much lower than the previous 2005 guideline levels. So these values for the pollutants we measure, which is PM2.5 and carbon monoxide, will be a reference to the concentrations we'll measure at your schools and in generally in urban air. So we've got the koalas in the 5 schools which are part of this program. Southport for 3 years operated, Longreach for 2 years, Mackay 7 months, Mansfield in Brisbane 4 months, and the Gap in Brisbane 2 months. Work, I'm very pleased to report that all the koalas operated successfully, and we are talking about this period since we've last talked. All the data have been received in our database, and here we'll present data just for the month of September 2021, and based on this, we'll point out to some aspects of the data and what does it mean in terms of the sources and the concentration levels. So let's look at your school.